So the next big thing that we talk about in this course is what we call a library of functions. Throughout the course, we're going to be talking about many different types of functions, including polynomial functions, rational functions, radical functions, exponential and logarithmic functions, trig functions, and so we really need to get a feel for some sort of basic or foundational functions, okay, or fundamental functions, I don't know. So these a basic set of functions that we can build off of, okay? So that's where we're going to go with this video. So we'll call this a library of functions, and it's just a list of different types of functions that are other functions can build off of, and then it gets us a little practice with finding things like the domain and the range and the intercepts, and just some other features, some symmetry maybe in those functions. Okay, so let's start off with one of the more basic ones, and that is the function f of x equals a constant. I'm going to call it b, okay? I think that's what the book calls it. Yeah, f of x equals b. Now this is what we call a constant function. Where b is just a real number, okay? Now, there is no x in that function. It seems kind of weird. F of x equals something that doesn't have an x in it. But basically what that means is that every output is a fixed value of b. So no matter what x is, when you plug it in, you always get b as your output, whatever that number is, okay? So, you know, as an example, if you had f of x equals 5, well then, no matter what the input is, every input will give you the same output of 5, okay? So output 5, input 2, output 5, input 3, output 5, input negative 70, output 5. 5 is the output, it's guaranteed no matter what. It's a constant function, and the graph of it is going to be a horizontal line 5 units high, okay? Because every output, every y value is 5. As a general principle then, any constant function is going to be or have a horizontal graph. So if these are my x and y axes, then the graph of that function would be a horizontal line b units high, okay, whatever b is. It could be up, it could be down. If b is negative, it's below the x-axis. This is just a general arbitrary constant function. So it's going to be a horizontal line. Okay, now the y-intercept of a constant function is just that b value. So the y-intercept here is going to be 0, b, whatever b is. If it's 5, it's 0, 5. And the x-intercept, well, there is none. There's no place where this graph is going to hit the x-axis unless our b value is 0, in which case the horizontal line is the x-axis. So if you had f of x equals 0, then your graph is the x-axis, and every point is an x-intercept. Okay, but generally speaking, I'm going to say there's no x-intercept. And then again, except, can't spell, C-E-P-T, except if b equals 0. Okay, and again, if b did equal 0, then every point would be an x-intercept. Okay, there's no, well, if you think about local max and local min values, there are actually an infinite number of each. Every point on this graph is technically an absolute max and an absolute min, and a local max and a local min. Because of the way those things are defined, every point in the graph is either greater than or equal to every other point in the graph. And every point in the graph is also less than or equal to every point in the graph. And so you could consider every point an absolute max or an absolute min. Seems kind of weird, but it's true. Then, let's see, what else could I say about this graph? Oh, it is never increasing nor decreasing because it's constant. It's constant everywhere. So it neither increases nor decreases. What's really interesting to me is the domain and the range. The domain on this is all real numbers because the x values go in either direction, and there's no limit to what I could plug into this. I know the output's always going to be b. There's nothing undefined here. So the domain is all real numbers. The range, however, is a little different. The output, the range is always the outputs, right? And the output is b. There's only one output. So the range is just the set containing b. There are no other outputs to this graph. Okay, so it's a very simple range. Okay, and this seems to be probably the most basic of all of our functions. It's just this constant function. It's a 0-degree polynomial, if you know anything about polynomials, which we will be talking about more later in the course. But it's you know, a nice basic function. Now, going one step further than that is another linear function. This time we're going to call it f of x equals x instead of b. It's just the variable rather than the constant. All right, so let me get rid of some of this. So we're going to look at f of x equals x. This is what we call the identity function. It identifies exactly the inputs and the outputs. The input and the output are the same. If I plug in a 4, I get out a 4. If I plug in 32, I get out 32. No matter what I plug in, I get that out. So this is what we call the identity function. Okay, it's an identity function. And the graph of this thing, if you recall, your slope-intercept form of a line, if you remember y equals mx plus b, this would be in slope-intercept form with a slope of 1 and a y-intercept of 0. And so it ends up being, going through the origin, because 0, 0 is on the graph, and it goes up at a 45-degree angle to the right and down to the left at a 45-degree angle. Okay, it goes up 1 over 1 if you think about a slope. In addition to that, you could think of, whenever you plug in, if you plug in a number, you get out the same number, like 1, 1, 2, 2, 3, 3. Those are the ordered pairs. If you go over 1, up 1, over 1, up 1, you go over 3, up 3. No matter what it is, you're always going over and up the same amount to get to the next point. And so that gives us our, our diagonal line there. The y-intercept on this one, the point at which the graph goes through the y-axis, is the origin, 0, 0. And so is the x-intercept, interestingly. In fact, oops, I don't know what I'm doing there. Anytime the graph goes through the origin, that's going to be both an x-intercept and a y-intercept. Again, this one has no absolute or local max and no absolute or local minimum because the graph shoots up indefinitely in both directions and never wavers, doesn't have any turning to it. Okay. The domain is, of course, all real numbers. You can plug anything into that function and you can get an output. And the range is also all real numbers because whatever you plug in, you're going to get out. So if one is all real numbers, the other one's got to be. So both the domain and the range are going to be all real numbers. Okay, both of those are going to be true. Okay, so that gives us a good base. Now the next basic function we're going to talk about is called the squaring function. We're going to start increasing the degree of the polynomial now. And so we're going to look at a second degree, because that's a first degree. We looked at 0 and 1 degrees. Now we've got a second degree, x squared. So f of x equals x squared is going to be your parabola. This is called the squaring function. And I assume you guys know something about parabolas, at least the general shape of them. And so in this case, the general shape of this parabola is going to be, well, it's the square of every number. So if I plug in a 0, I get a 0 out. If I plug in a 1, I get a 1. Plug in a 2, I get a 4. Plug in a 3, I get a 9. And so on the right side, it's a curve that curves up and to the right. And on the left, you get a mirror image, because if I plug in -1, I get out 1. Plug in -2, I get out 4. Plug in -3, I get out 9. So it's the mirror image just on the other side. Okay. Okay, so this is what we call a parabola. This one has some symmetry. Oh, I forgot to mention symmetry in the other ones. The constant function has y-axis symmetry. I should have mentioned that. The identity function has origin symmetry. I should have mentioned that as well. I'll write that on here while I have it up. Remember, origin symmetry results in it being called an odd function. Y-axis symmetry results in it being called an even function. So here we have y-axis symmetry. So we would call that an even function. Okay. Let's see, what else we have? Oh, intercepts. Again, the x and y intercept are both the origin. And the domain and range are, we've got to work on those. Those are a little bit different. The domain actually is the same. It is all real numbers, but it's the range that's different. So domain on this one, you can plug anything in to a squaring function and raise it to the second power. You're going to get something as an answer, so that's okay. The outputs, however, when you square a number, you always get a positive or 0. You never get a negative. So there's a restriction on the domain here, or on the range, I'm sorry, on the range. So you always are going to get a positive or 0. So that would make 0 to infinity the range. Okay? No negative numbers can come out from that. Now the exception is if you were plugging in complex numbers, you could obviously square a complex number and get out negatives, but we're not worried about complex numbers here. We're strictly working with real numbers in this class. Okay. All right, so that gives you some idea of the squaring function. Now let's look at the next one. You can probably assume it's going to be the cubing function, right? Go 1 degree higher. All right, so we're going to have f of x equals x to the third. That's the cubing function. And of course, this one's a little bit different. The graph, if you think about positive values when you cube them, like 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. As you cube a number, those bigger numbers get bigger, right? And so you end up with a graph that actually looks very similar to a parabola on the right. It's just going to actually increase faster than the parabola did because when you cube something, it grows bigger. Except for between 0 and 1. Between 0 and 1, if you cube a number, it actually gets smaller. For instance, 1/2, if you cube it, becomes 1/8. And so you end up kind of leveling off, flattening out at the bottom. Now on the left side, when you cube a number, a negative number, you get out a negative number, which is different than with a square. When you cube when you square a negative, you get a positive. When you cube a negative, you get a negative. And so you're going to have a mirror image, but it's going to be down and to the left. The cubing functions, therefore, do not have y-axis symmetry. They have origin symmetry. Okay, so this is origin symmetry, which makes it an odd function. Okay. Again, the x and y intercepts are at the origin, so that's nothing new at this point. So the y-intercept and x-intercept are going to be at the origin. The domain, like all the rest of the domain so far, is all real numbers. No matter what I plug in, I can always cube a number. So the domain is negative infinity to infinity. And on this one, the range is also negative infinity to infinity because this graph goes up indefinitely and down indefinitely. Okay, so the range is going to be all real numbers. So there's no limitation to what you can get out from a cube like you can with a square. Square is limited because you can only get positives or 0. A cube, you can get negatives, so that's okay. We got to include those. Okay. All right, so that gives you a pretty good understanding. Now, if we continue to increase the power on the x, you get x to the 4th, x to the 5th, you're going to have very similar shaped graphs. All of the even powers are going to have y-axis symmetry. The only difference between x to the 4th and x squared is that the graph will increase faster at the tails, and it will flatten out more in the middle. Okay, for the same reason I just mentioned on the x cubed. So if I wanted x to the 4th, it would be a little bit flatter at the beginning, and then it would shoot up faster, flatter and then shoot up. It almost starts to look like a rectangle when you get the powers really high. If I had like x to the 10th, it would be a very, very flat middle and then a very steep increase. It would look something like that. And so it just gets steeper and steeper the higher the power. Same thing for the cubing, or for the odd powers, right? Like the cubing function, if you go to the 5th power, 7th power, it's going to have a similar shape to this. It's going to have origin symmetry, but again, in the middle, it's going to flatten out a little bit more, and on the ends, it's going to go steeper. Okay, so similar idea. The higher power functions are not actually in this section, just kind of some neat information I figured you may be interested in. Okay, let's look at another one of our basic functions. So we're going to get away from the polynomial or the power functions. And instead, we're going to get into, let's see, what's next? Oh, the roots. Okay, I dropped my marker. That's where it disappeared. We're going to get into the roots. So something like f of x equals the square root of x. Okay. Well, square roots are a little bit interesting because you're limited on what you can plug in this time. You can't plug in negatives to a square root because you get complex numbers out. And we don't want to deal with complex. We're going to deal with just real numbers. So instead, this is called the square root function. And we're going to be limited then to just 0 as an input and positive inputs. When I start to plot these things, you know, we plug in a 0, the square root of 0 is 0. Square root of 1 is 1. So you go over 1 up 1. But then the square root, you know, if you start dealing with like square root of 2, they're irrational numbers. They're harder to, you know, find those and plot those. You need maybe a calculator to come up with some decimals. But you can get to some nice ones, like square root of 4 is 2. So if I go up 4 units, I'm only going to be going up 2. And so this graph has a definite curve to it. In fact, it's going to be parabolic. Okay, so it's a parabola, essentially, half of a parabola laying down. So opening out to the right instead of opening up. What's interesting about this is that you don't have the bottom half. So it's like half of a parabola. And the reason, again, for that is because when you plug in a positive, you take the square root, you're going to get a positive. You can't get 2 options out of a square root like that. All right? It's built that way. This is the principal square root here. So, let's see. So, is there symmetry to this? No. There's no x-axis symmetry, no y-axis, no origin. There's no symmetry at all. So this one has no symmetry. Again, the y-intercept and the x-intercept are both 0, 0, so we don't have any issues there. The domain, remember, cannot include negative numbers. It's just 0 and positive numbers. So the domain here is going to be 0 to infinity, and then the range, well, the range on this one is, again, 0 to infinity. It's everything shooting up and to the right. or from 0 up. Okay, so again, you can only get out positives or 0 from a square root. Okay, so that gives us our square root function related to the cube. We're going to have a cube root. Okay, so cube root function is the next one on the list. Okay. All right, so the cube root function is kind of interesting because it, kind of like the cube function, can work with negatives. Okay, you can take cube roots of negatives. Cube root of -8 is -2. And so it goes through the origin again because the cube root is 0, 0. It's going to shoot up and to the right, you know, similar to the parabola, except it's going to be a little bit flatter at first, a little steeper, and then it's going to flatten out a little bit more. But you're going to have negative values. Plug in a negative, you're going to get out a negative for a cube root. And so you'll have this reflection across the origin again. So this does have origin symmetry. Which makes it an odd function. Okay, origin symmetry makes it an odd function. One thing I might might make a note of here is that you may see some patterns with the odd and even functions. With even functions, they tend to be things with even powers, right? Our x squared and our x to the 4th. And even our constant function is really an x to the 0, kind of a 0-degree polynomial. They all have even function or even powers on x, which makes them, you know, symmetric with respect to the y-axis. The odd powers, things like you know, your x to the 1, x to the 3, x to the 5, cube root of x, those odd powers and roots are going to have origin symmetry, generally speaking. Now, that's not always the case, right? The square root does not have y-axis symmetry, so I can't quite say that as a general principle for everything, but it often is the case that things that have all even powers will often have y-axis symmetry. Things that have all odd powers will often have origin symmetry. Again, that's not always true, but that's a good way to, you know, kind of identify those things. And I believe that's where the name even and odd come from. Okay. All right, so here again, the x-intercept and the y-intercept are the origin. This is getting to be redundant, right? Okay. The domain on this one, though, is all real numbers because you can plug anything in. And same with the output. This graph extends vertically up and down indefinitely. So both the domain and the range are going to be all real numbers. Okay. All right, so the next function, of course, and I should probably generalize this too, if you were to extend these roots to be 4th roots, 5th roots, a very similar pattern will occur with the roots as they did with the powers. Basically, with a higher root, with an even root, you just get this one-sided graph, but it's going to be steeper at the beginning, and it's going to level off flatter at the end. Same thing with the odd roots. It'll be steeper in the middle here, and it'll be leveling off to the right and to the left. Okay. All right, so then let's look at another type of function. So we've got our powers, our roots, our lines. Let's see, another common one. There's a couple here. Where are they? I guess the next one I want to talk about is the reciprocal function. F of x equals 1 over x. Okay, this is what we call a reciprocal function. Remember, 1 over a number is its reciprocal. So if I wanted 1 over 5, it's 1/5, right? So if I wanted 1 over 2/3, it'd be 3/2. So you always get the reciprocal of the function, or of the number, when you put 1 over that number, or divide by that number. The graph is interesting. It's a little bit harder to explain where this comes from. You almost need to plot more points than what I'm going to do. I'm just giving a brief overview. One thing to remember though, when you plug in a positive number, 1 over a positive, positive over a positive is positive. So you're going to get points in the first quadrant because you plug in a positive, you get out a positive. Also with negatives, if you plug in a negative, 1 over a negative is negative. And so if you plug in a negative, you get out a negative. So you're only going to have points in the first and third quadrants on this one. If you plug in 0, what's 1 over 0? Well, it's undefined. So there's no 0 in the domain. So there's not going to be a point at the origin like there has been, or at all on the y-axis. In fact, there's going to be no y-intercept here. And that tells us right away that the domain is all real numbers except 0. So we could write that in as x such that x is not equal to 0. Right? I can't plug a 0 into that function. It's the only thing I can't plug in, but I can't plug that in. Okay. Now what's interesting is that when you plug in large numbers for x, you get very small outputs. The larger you plug something in, like if I plugged in 1,000, 1 over 1,000 is like 0.0001 or something, right? Maybe I'm off by 1, but it's a very small number. The larger the input, the larger the denominator, the smaller the number. And so this graph is going to get very small, but staying positive, right? If I plug in a 1, 1 over 1 is 1. That's the only point in that first quadrant that kind of doesn't move, right? You plug in a number, its reciprocal is itself. But after that, every point to the right is going to get closer to the x-axis because it's getting smaller and smaller. The farther you go from the origin, the smaller that number gets. But it's always positive because it's always a positive over a positive. You can never hit 0 by doing that, okay? You can also never get negative by doing that. So this graph gets closer to the x-axis without actually hitting it. It's called an asymptote. We're going to say that this has a horizontal asymptote at y equals 0. Y equals 0 is the x-axis, right? That's that constant function on the x-axis there. It also, the reverse of that is also true. So the closer the number, the denominator gets to 0, the bigger its reciprocal. So if I plug in a number like 0.1, the output is 10. 0.01, the output is 100. And so you get the opposite effect going on where small inputs give you big outputs. And so the graph is going to be increasing very rapidly next to the y-axis or near the y-axis there. And then of course, if you want to find a mirror image of that, you just plug in the negative numbers and you get the same sort of behavior but in the third quadrant. I won't go through all the details there. We'll go through -1, -1. And we'll get close to the x-axis and close to the y-axis. And so in this graph, you actually do have origin symmetry. Every point on the graph will be able to reflect through through the origin to find another point on the graph. I didn't draw that very well. Okay, so this does have origin symmetry. Which makes it an odd function. And notice the power on the x, it's x to the 1, so there's an odd power there, but it kind of makes sense. In addition to that, the range is all real numbers except 0. 0 is the only thing I can't hit. I can hit every positive number and I can hit every negative number in the range vertically, but I never hit 0. 0 is an impossible output from this fraction. In fact, the only way to make a fraction equal to 0 is if the top is 0. But the top of this is always 1, so I can't have that. So here the range is actually the same as the domain, but I'm going to use y's instead of x's because it's a range. So I'd say the range is y such that y is not equal to 0. Okay? So those two sets are essentially the same. Okay, so that gives us our reciprocal function. That's the last of the basic functions. I'm going to stop this video, go to the next one. The next video I'm going to start to talk about piecewise functions and some very interesting functions that are kind of defined differently over different portions of their domain.